Good morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department and Institute of Aeronautical Engineering. The topic for today's discussion is finite differences. In the first video, the previous video, we have seen how to derive the finite differences using Taylor series. Now we will see a different approach in this class. Now in that, the one which we have used, the Taylor series, we have derived the finite differences for forward difference, backward difference, all those things, central difference, and first order difference and second order accuracy difference, all those things we have seen. Now say suppose if the grid is like this as shown in the figure. Now the grid starts from point 1 to 3 like this. Now the distance between the two grids is delta y, so it is a uniform grid. Now in this kind of scenario, say suppose if I want a second order accurate finite difference approximation at point 1, which is on the boundary. So if I want to use the second order accuracy equation, that which we derived from the Taylor series, it is like this. Okay, so here u2 is at point 2, so here I will get u2. But if I want a value at this point, which is at 2 dash, which is outside the boundary and whose values which we don't have, then in this kind of scenario, our Taylor series fails. The derivation that we have got from the Taylor series, that is central difference equation, fails, because we don't know the value of the velocity u at this particular point 2 dash. Now why? Because it is outside the computational domain. Okay, this is the computational domain which we are talking about, and this point 2 dash is outside the computational domain, and for which we don't have the values, and so our central difference equation fails in this kind of scenario. Now in earlier days, when there was no other method for finding the finite difference expressions, what they assumed is this u2 is equal to u2 dash. Okay, they assumed that the value of this 2 dash is same as the value of u2, and they have solved the finite difference method. They use this kind of approach in the finite difference method, and this method is called the reflection boundary condition. So what is the reflection boundary condition? This is the boundary, and we have a point on the other side of the boundary, that is at 2, and we are taking a mirror reflection as 2 dash, and we are solving we are finding the finite differences at point 1 of second order accuracy. So this is called the reflection boundary condition. Now after some time, what they arrived is there is called as polynomial approach. Okay, to avoid this kind of difficulty where we have to use the boundary reflection condition, instead of that, what they have derived a polynomial approach for finding the finite differences for each grid. Okay, finite difference expression for each grid. Now in this polynomial approach, what we do is it is a second procedure. The first procedure generally used is Taylor series approach, and the polynomial approach is the second approach, which generally is done for the boundary and the nodes at the boundaries. Okay, now here what we do is the coefficients that we have are expressed in polynomial equations. Okay, so this is in this u is the dependent variable and y is the independent variable, and this dou u by dou y what we are doing, this u we are expressing as a polynomial expression of the y. So as I suppose you can write this as u into u is equal to a plus by plus cy square, something like that we can write. So this is a polynomial expression. Now what we are doing is we are expressing the dependent variable in terms of the independent variable as a polynomial series, and using that we are finding what is the dou u by dou x or dou square u by dou y square, like what is the approximate finite difference approximations for dou u by dou x and dou u by dou y from this this polynomial that we have selected. What we are doing here is the first what we will do, you will apply y value at 1.1, and we will apply the y value at 0.2, and we will apply y value at 0.3. Like this we will apply, and then we will solve the equations for a, b, c constants, and then we will find what is the dou u by dou x, or dou u by dou y or dou u by dou x, whatever is the condition. Whatever, if the x is the independent variable, then we will get dou u by dou x. If y is the independent variable, then you will get dou u by dou y. Now here in this example that we are considering, it is along the y axis. So the grid is along the y axis. So we are finding dou u by dou y in this particular example. Now this is the alternative method other than using the reflection boundary condition for finding the second order for accurate differences. Second order accurate differences for the element at the boundary. Okay. Now we will see how this approach is about using this example that we have considered. Now consider a example u is equal to a plus by plus cy square. This is the second order polynomial. Second order polynomial, why it is called second order polynomial? Because the order of the equation is 2. The order of the equation is 2, so we are calling it as second order polynomial. Now the yj, say suppose yj is at boundary, yj is at boundary, then it is yj plus 1 and this is yj plus 2, j plus 1 and j plus 2, like this will go from y. Now so what we have to do here, we have to substitute the values of y at point 1. Now at point 1 the value of yj is equal to 0. So this is the yj value. So at point 1 yj is equal to 0. If I substitute yj is equal to 0, this will become 0, this will become 0, then uj is equal to a. So we found what is the value of uj. Now in other words, we can say that we can from this we can find what is the value of this constant a. So the value of the constant a is uj. Now if I substitute the values at grid point 2, now at grid point 2 what is the value? Here the value is 0, and from here to here the distance is delta y, so it is at 0 plus delta y. So the value at point 2, the value of y at point 2 is equal to delta y. Okay. Now if I substitute this delta y in this equation, then I will get the value of uj plus 1. Okay, because we are using yj plus 1, you will get the velocity at j plus 1. Now at j plus 1, the value of yj plus 1 is delta y. So if I substitute that here, it will be delta y and this is delta y square. The equation will be like this. Now if I repeat the same thing for point 3. So what point 3, what is the value? Here it is 0, here it is 0 plus delta y, and here it is 0 plus 2 delta y, because we are keep on adding the delta y terms here for the value of y. So the yj plus 2 is equal to 2 delta y. If I substitute the yj plus 2 value 2 delta y in this equation, what I will get? I will get uj plus 2. we are using yj plus 2, so we are getting uj plus 2. So what is the value of uj plus 2? It is here in place of y we have to put 2 delta y, in place of y square we have to put 2 delta y whole square. If I substitute like that, we will get three equations. This is the equation 1, this is equation 2, this is equation 3. Now if I solve these three equations, what I will get? I will get the values of the constant a, b, c. We will see how to do that. Now here, this is the equation that we have considered, and we want the values of a, b, c constants. Now uj is equal to a, that we have derived when yi is at point 1. At yj plus 1 is at point 2, we got this equation. Yj plus 3 at point 3, yj plus 2 at point 3, and then we got this equation. Now if I solve these equations, so how to solve? You can use you can subtract this, then this will go, and if you subtract like that, you can manipulate these equations. If you manipulate these equations, you can get what is the value of b and c. We will see how to manipulate this equation, one equation. I mean, for we will solve for b, so that the similar way you can solve for c. Say suppose if I am solving for b, okay, how to do that? You can use the here this is delta y and this is 2 delta y. So this is more and this is less. So I am multiplying with minus the above equation. If I multiply the above equation with minus, what I will get? I will get is uj plus 2 minus uj minus 2. Okay. And so what I can do is I can eliminate this c, because we don't know c. A is known, so a will keep, and we will eliminate the c value. So if I want to eliminate the c to find b value, how to do? This is delta y square and this is 2 into delta y whole square. So if I multiply this entire equation with 4 and subtract that from this equation, then this will be eliminated. So if I do like that, what I will get? I will get is uj plus 1, 4uj plus 1 minus uj plus 2 minus uj plus 2, and here this one is 4a and this one is a. So I will get equal to 3a, and here what I will get? Here it is 4 delta y, here it is 2 delta y, so it will be plus b into 2 delta y. Like this I will get. So if I do like this, now what I have to do? I have to substitute value of a. So what is a value? It is a uj. So what I will get? Minus uj plus 2 plus 4uj plus 1, and this one will go this side. So it will be minus 3uj divided by 2 delta y. Like this I will get. So this is the equation I got for b. Okay, if I simplify this 3a, if I will bring this side, and 2 delta y I will bring this side, it will go to denominator. So I will get this equation. So in this way I can derive the value of b from these two equations. Similarly, if I want to find the value of c, what I have to do? The c I have to keep, and I have to eliminate b. So if I want to eliminate b, so what I have to do? I have to multiply this equation with 2 and subtract from this equation. So if I do like that, what I will get? I will get 2uj plus 1 will be there here, and minus uj plus 2 will be there, and what else will be there? Here I am multiplying with 2, and here this one will get cancelled, because this is 2 delta y and this is 2 delta y, and here it is 2 delta y square, and here it is 4 delta y square, because 2 square is there, so it is 4 delta y whole square, 4 delta y square. So in that case, what will be this value? It is minus c 2c delta y whole square. So okay, so this is equal to, and here this is 2a and this is a, so I will get a here. Okay, I am subtracting this equation from this equation. So here 2uj plus 1 minus 2uj plus 1, j plus 2, and here 2a minus a is a, and here 2 delta y whole square minus 4 delta y whole square, I will get minus 2c delta y whole square. Now what I will get? This a I will bring this side, and minus sign I will multiply. If I multiply like that, what I will get? I will get uj minus 2uj plus 1 plus uj plus 2 divided by 2 delta y whole square. So like this I will get the value for C. The same thing you can see here, it is a 2j plus 2 minus 2j plus 1 and plus uj. So this is the procedure for finding the solution for these two values of these two constants using this polynomial approach. Once you get the values of a, b, c and all, what you can do? You can find out what is the expression for dou u by dou ay and expression for dou square u by dou y square. How we will see? You have the value for b and you have value for c. So if I differentiate this equation with respect to y, if I differentiate this equation with respect to y, what I will get? This is constant, it will become 0, and this is y term is there, so it will become b, and it is 2cy square. So if I differentiate, it will become 2cy. So this is the equation. So in this case, now what I have to do? I have to apply the boundary condition. Y is there. If I apply the boundary condition yj, what I will get? Dou u by dou y at j is equal to b. Now dou u by dou y at j means the partial differential equation dou u by dou y is for node 1. So the dou u by dou y for node 1 is equal to b. Now already we have found out what is the value of b. If I substitute the value of b, it will be like this. Now here you can see we are using only the terms which are ahead of this one. We don't need any term below 1 which is not 1. Below 1 we don't know the values, and we don't require those values here in this kind of scenario. Now that is the reason what we can say this is a one-sided equation, one-sided finite difference equation, because we are using the values of 1, 2, 3 only for finding the value of dou u by dou y at 1. Okay, we are using the values of 1, 2, 3 which are on one side of the point 1, and we are finding the values of dou u by dou y. So that is why this equation is called one-sided finite difference equation, and it is at boundary. This is our main concern, because if I use the Taylor series at boundary, we cannot find the finite difference expression which is of the order of order of 2. And now we'll see whether it is the order of this equation is 2 or not. Okay, the second order accurate for finite forward difference expression obtained from Taylor series. It is similar to second order accurate finite forward difference expression obtained from Taylor series expansion. Okay, we will see whether the statement is true or not in the next slide. So, and this approximation is classified as second order accurate for dou u by dou y. And why we are using it, why we are calling it as a second order accurate, we will see now. See here, this is the polynomial that we used for deriving the value of dou u by dou y. Now if I consider the Taylor series expansion at point 1, if I consider the Taylor series expansion at point 1, it will be uy is equal to u1 into dou u by dou y at 1. So everyone at 1, dou u by dou y at 1 into y, dou square u by dou y square at 1 into y square by 2 plus dou cube u by dou y cube into y cube by 6. Like this I will get the Taylor series. Now in this equation I have first term, second term, third term. First term, second term, third term. So the order of accuracy is delta y square. Okay, the order of accuracy is delta y square. Why? Because we are eliminating the y cube terms. We are eliminating the y cube terms. This is the error that we are considering for this equation for writing in this form. So it is called a second order accurate equation. Now here we derived u1, u2, u3 or uj1 plus uj plus 1 and uj plus 2. All these values we derived using this second order accurate equation. So the obtained dou u by dou y at j at node 1 where y is equal to where it is yj, the equation obtained is of the order of second or order of 2 since we are neglecting the power 3 terms in the Taylor series. So this is called the second order accurate finite difference equation, finite difference expression approximation at the boundary. Now we will see what is the value of dou square u by dou y square. So in order to get that, what I have to do, I have to differentiate this 2 times. If I differentiate this once, what I got, b plus 2cy dou u by dou y is equal to dou u by dou y is equal to b plus 2cy. This is the equation that we got. Now if I differentiate this further, what I will get, this will become 0 and this one will become 2c. So dou square u by dou y square is equal to 2c. So this is the equation. Already we found out what is the value of c, and if I substitute that, I will get what is the value of dou square u by dou y square. Okay. Now this is similar to the first order forward difference approximation. Okay, this is equal to the first order forward difference approximation because we are neglecting, in the previous one we have neglected y cube terms. Okay, dou cube u by dou y cube, that one we neglected, so it is called second order. And in this what we are neglecting, the higher order terms, we are neglecting dou square u by dou y square. Okay, so sorry, here we are neglecting the y. There we neglected y cube terms. Here we are neglecting the y square terms. So it is called the first order forward difference equation. So here why we are calling it as first order, forward difference, because we are using the terms after this one. We are using j is our present term. We are using j plus 1 and j plus 2 for finding the finite difference at 1. That is the reason it is called the forward difference approximation. And why it is called the first order? Because the y square terms are all neglected in the Taylor series, and that's why it is called the first order term. So this is about the finite difference approximation when the grid is equally spaced. So here the grid is equally spaced, so it is called uniform grid or equally spaced grid. Now if I want to find what is the value for a non-uniform or unequally spaced grids, what is this? It is a non-uniform or unequally spaced grids. So here it is delta y, here it is alpha into delta y, and now next one will be alpha 2 alpha into delta y or alpha square into delta y. Like that it will change. Now in this kind of scenario, if the consecutive, the differences between the distances between the two nodes is not equal, then how to find the finite difference approximation? Now again we'll use the same polynomial of second order. We have seen why it is called second order, because we are neglecting y cube terms. Since we are neglecting y cube terms, it is called the second order polynomial expression. Now at origin it is a yi or yj here. If at origin it is yj, and at yj it is a 0. Okay, yj is 0 at this point, and here it is a 0 plus delta y, and here it is a 0 plus delta y plus alpha delta y. Like this it will go on increasing, and the next one will be 2 alpha delta y, and after that it is 3 alpha delta y. Like that it will go. Now if that is the case, how to find the value of dou u by dou ax or dou u by dou y in this case at point 1? So what we have to do, we have to substitute the values of y in this equation. So at point 1 y is equal to 0 or yj is equal to 0. Now if I substitute that, this will become 0, this will become 0, so uj is equal to 0. Now at point 2, the value of y is delta y. If I substitute the value of delta y here, y is delta y. So what will happen? U is equal to a plus b delta y plus c delta y whole square. So like this I will get. Now at this point, so what is the value of this one here? 1 plus alpha into delta y. What I am taking? I am taking delta y common. So it will be 1 plus alpha into delta y. If this is the value, what I will get? I am substituting the y is equal to 1 plus alpha into delta y. So if I substitute like that, what it will be? A plus b into 1 plus alpha into delta y plus c into 1 plus alpha whole square into delta y whole square. So like this I will get. So these are the three equations, 1, 2, 3 equations we got by substituting the values of y, the independent variable, at point 1, point 2 and point 3. Using these three values, we can find out the values of a, b, c as we did in the case of the uniform grid. So these are the equations that we got, 1, 2, 3, and if I got value of a, and I have two equations to find the values of b and c. Solving these two equations, I can get these two values, and this is a b value and this is a c value. Okay. Now once we know the value of b and value of c, we have to find out what are the values of dou u by dou x and dou square u by dou x square. So what we did, we differentiated this one time and we got it is what is the value of and substituted the value at y is equal to 1, then we'll get what is the value of b here. Now here if I differentiate this one time, what I will get? I will get b plus 2cy. Now if in b plus 2cy, if I substitute y is equal to 0, I am substituting y is equal to 0 in this equation. If I substitute y is equal to 0 in this equation, what I will get? I will get this will become 0, so I will get dou u by dou y is equal to b. So dou u by dou y at j. Why we are calling it at j? Because we are putting the value of y at point 1. So it is a point at point 1 yj is equal to 0. I substituted that, so it is dou u by dou y at j, and that is equal to b. And we have already derived the values of a, b, c in the previous slide, and if I use that, it will be dou u by dou y at j. Similarly, if I second differentiate this, what I will get? So the first differentiation is b plus 2cy, and that is equal to dou u by dou y. Okay, now if I differentiate it again, this will become 0 and y will go, so it will be only 2c. So if it is a 2c, what will happen? I will get dou square u by dou y square is equal to 2c, and that c value, you know, if I substitute that c value, I will get dou square u by dou y square is equal to this equation. And this is the first order finite forward difference expression. Why it is called first order? Because we are neglecting the y square terms. It is called the first order. And why it is called forward? Because we are using the elements which are after the present one. This is the present one, and we are using u1, u2, u3, the elements which are forward ahead of the element 1. That is why it is called the forward difference. Okay, so this is about the polynomial approach that we need to discuss. So in summary, if we want to see what we have seen, the Taylor series, the expressions derived from Taylor series for the finite differences of the partial differential equations or partial differential terms, they cannot be expressed for the boundary. If I cannot express the value of dou u by dou x or dou y at boundary, if I want a second order accurate expression, because the second order accurate expression for this requires a value below this point 1. Okay, so in that case, the value of this point below the point 1 is outside the computational domain, and we cannot get it accurately. And the previous before the usage of the polynomial functions came into existence, the scientists used, the mathematicians used the boundary reflection conditions, and they applied the u2 as the value at this point, and that is in order to avoid that that difficulty, what we are doing is we are using the polynomial approach, and we since we need a second order accurate one, we have selected a second order polynomial, and using that second order polynomial, we substituted the values of independent variables at point 1, 2, 3, and we found out what are the values of a, b, c, and from that what we did, we found out what is the value of dou u by dou y and dou square u by dou y square, and the value of dou u by dou y what we got is a second order forward difference approximation, and the value of dou square u by dou y square that we got is a first order forward difference approximation. With that, I am closing the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.